Hello, everybody. If you are watching this, then that means that, well, hopefully you are ready to learn about some probability. You just took the quiz a little while ago. Some of you had to deal with some typos. Sorry about that. But hopefully everything went well on that quiz, and we can certainly talk about um, questions if you have them on Monday. In the meantime, we need to talk about probability. If you are here watching this only because of that little C that shows up, if you know some stuff about probability and you've heard of union and intersection, but that little C is something that you've never seen before, then skip ahead. It's going to show up in the last few minutes of this lesson. But in the meantime, if you don't know a lot about probability, let's talk about probability. All right, so I'm sure you've done some basic probability in previous years of mathematics, elementary school, middle school. But just a refresher, when I say the probability of something, it's the chance of something happening. It's a measure of the likelihood of something. You might say that the probability of the Timberwolves winning their game tonight is not very large. Especially since I know they played last night. So the probability of winning tonight is probably 0 because I don't think they have a game tonight, which I guess brings me to my last thing. A probability can never be less than 0. A negative probability does not make sense, nor does a probability greater than 1. What is the probability that the sun is going to come up tomorrow? Well, I guess it could be cloudy. Bad example. What is the probability that the temperature in Minnesota is going to be lower than 90 degrees Fahrenheit tomorrow? Well, maybe not exactly 1. I suppose there could be some crazy weather behavior, but pretty close to 1. Never greater than 1. Something that is absolutely certain would have a probability of 1 or 100%. Which brings me to my third point. We can express probability as a fraction, a decimal, or a percent. The probability when I flip a coin, the result is heads. I can say that it's 1/2. As a fraction, I can say that it's 0.5 as a decimal, or I can say that it's 50%. And I would say that all three of these things are mathematically equivalent. 1/2 is the same as 0.5, which is the same as 50%. Actually, writing it as a fraction is usually what's going to make sense, because when we talk about probability, we've got the number of ways that something can happen divided by the total number of possibilities. So I guess when I flip a coin, there's 2 possible outcomes. One of those is heads. And so my probability of flipping a coin and having a result of heads is 1 out of 2, 1/2. If I say that there is a scholarship, there's a $1,000 scholarship, and there are 6 students that are going to be chosen out of 40 students who applied, who are eligible. And I say, what's the probability of those 40 people, those 40 students all signed up for this? And there's no essay, there's no judging or contest or anything like that. It's just there's 40, and they're going to put those 40 names in a hat and draw 6 of those names out. The probability is simply 6 out of 40. Well, this is an honors level functions and trig class. So let's simplify a fraction like this. Let's reduce that and call that 3/20. And that is my probability. The probability for any one of those people is 3/20. If you want to convert that over into a percent, you could do 3 divided by 20 on your calculator and find, let's see, that must be 15%. 0.15 would be okay also. Or if you want to say 15%, any one of those would be okay. I'm going to leave the 3/20 circled. That's probably how I would prefer something like this. But if I'm one of those people, maybe 3/20, that doesn't register in my mind. Maybe thinking, okay, 15%, that makes sense to me. But better than 10%, it's less than 20%. And I know reasonably what those kinds of numbers mean. Some notation, and maybe this is why you are here looking at this video. You've heard of probability before, but you haven't seen these symbols before, maybe. Maybe you have seen them before. Well, and just in case you haven't, well, it's kind of a U shape. It certainly looks like a U, and it probably is a U shape because it stands for the union of two things. Or I guess it could be more than two things. When you see that U shape, think or. What is the probability if I'm playing a game of Monopoly and I roll the dice? What is the probability that I roll an odd number or a sum greater than 7? If I say or, I'm counting both of those categories, just like we had with Venn diagrams. Or means both of the categories, and if there's any intersection between them, that's okay also. Intersection, meaning I would think and you're going to see this symbol. It looks like an upside down U. And honestly, one of the things that I do to remember this is I'll think that that upside down U, if I draw that little crossbar on there, now it looks like the letter A, and that reminds me that that means and when I see intersection. So the U means union. That makes sense. The upside down U kind of looks like an A, which means and this thing and that thing. What is the probability of rolling a sum of 7 and an odd number is one of the dice or something like that? I would need both of those things to be happening at the same time. The intersection, just like it was with Venn diagrams. We'll do a couple examples. Starting with this one. If I choose a student randomly from this class, from the people watching this video right now, what's the probability of the following events? Their name starts with the letter J, the first name. The second letter in the first name is a U. Their name starts with J or the second letter is U, so the union of those. Or their name starts with J and the second letter is U, so the intersection. Now, expressing these in correct notation, when I say what's the probability that their name starts with the letter J, I might just use this notation. Uppercase P and then parentheses. It looks kind of like function notation, and it kind of is function notation. So this would be, what is the probability that their name starts with J, the probability the second letter in their name is U, etc. And so here I'm using this notation, the uppercase U shape to represent the or, the union of these two, and then the upside down U, or almost an A, representing the intersection and. So to help us answer this, my sample space looks like this. Hopefully I didn't miss anybody. I apologize if I did, but I would just copy down names from my seating chart. And so here, hopefully all of you are. Then I went through, and if we were doing this together, I might ask you guys, hey, type it in the chat if you see a name that starts with the letter J. Hey, let me know if you see a name that has the letter U. But since we can't do that in a video, I've taken the liberty of doing that for you. So here are all of the names. Ones on top, I was about to say that they don't matter, but that would be very belittling to most of the class. Not that you don't matter, but you won't be counted as far as starting with the letter J or having a second letter U. Now we see I've got them kind of sorted here. I've got these three over here on this side start with the letter J. Two over on the right side have a second letter U, and in between these three in the middle have both of them at the same time. So answering these three questions, what's the probability that a person chosen from this class has a first letter J? Well, we've got 6 of them. That's 6 out of, oh, I don't know if I said this, but there are, oh shoot, I think, yeah, 39 total people. So 6 out of 39. Just had to glance at my seating chart. We had 40 at the start of the semester, but I lost one. And then we'll reduce that. 6 out of 39 would be the same as, let's see, I suppose we can divide both of those by 3 and go with 2 out of 13. So the probability, if a random person is chosen from this class, that their name will start with the letter J is 2/13. The probability that the second letter in someone's name is a U, well, that's these people. And we've got 5 of them, so 5 out of the 39. And that doesn't reduce, so I'll just leave it like that. If you want to plug it in your calculator and calculate the percent, go for it, but I'm just going to leave it as 5/39. And then the trickier ones, the probability the name starts with J or the second letter is U. Now I'm counting all of these people. Those that start with J, those that have a second letter U, and those that have both. I'm counting all of them. Now I'm not double counting these people in the middle. They're just as important as the rest of the people in the class. And so I'm just counting. I've got 3, 4, 5, 6, 7, 8. And so my probability in this case is 8/39. And I do not believe that that reduces. The only factors of 8 would be 2 or 4, and neither of those is going to go into 39. So leave that as is. And finally, the probability of intersection, the probability that the name starts with J and has a second letter of U. Here is our intersection. This is the football shape in the middle of that Venn diagram. This would be 3 out of the 39, which does reduce. There's a 1 in 13 probability that a random person chosen from this class has a first name starting with J with the second letter of U. And so there we go. Julia, Judy, and Justin, you are the 1 out of 13. Okay. Another type of question might look like this. Now, the probability of having a boy is not exactly the same as the probability of having a girl. I know it's like 51-49 or something like that. I don't remember which one is more likely, but it's not exactly 50-50. For this problem, let's just treat it as if it's a 50-50 chance. Otherwise, the probability gets more complicated. Something that we could do, but maybe not on the first day of probability. What's the probability that a family who has 4 children has exactly 2 of each? You might think our sample space looks like this. We've got 0 boys, 1 boy, 2 boys, 3 boys, or 4 boys. And you would say, well, let's see, what's the probability that they've got 2 of each? We would say that it's 1 out of those 5. But this turns out to be not correct. It's more likely that you would have 2 of each than of having all 4 the same. My wife comes from a family. She is one of 4 girls in that family, and that is unlikely to happen. This is not our sample space. Our sample space is going to look more like this, where I've got to list all the different possibilities. First child could be a boy or a girl. And then given the first child is a boy or a girl, the second child could be a boy or a girl, etc., etc., etc. And so I've got these all listed out. There are 16 different ways, which, by the way, that's kind of a counting problem. If we say, what is the number of elements in the sample space, we would say that each element is one of 2 possibilities. So 2 times 2 times 2 times 2. Fundamental counting principle coming back to haunt us. Here we go. That's how we come up with the 16 members. And I'm going to strongly advise on your homework assignment when you're doing coin flipping problems and problems like these, list them out. I know it seems like a lot, but it actually doesn't take all that long if you're organized about it. But anyway, answering the question, what's the probability of having exactly 2 of each? At least the way that I've got this organized, they happen to all be kind of grouped together here. I've got too many boys over here. I've got too many girls over here. And then also too many boys, too many girls. And I shouldn't say too many. I guess too many to be the answer to this question is what I should say. You can't have too many boys or too many girls in your family. That's just silliness. Anyway, we got 2 of each in these 6 possibilities. So the probability, I'll say the probability of having 2 of each is 6 out of those 16, which reduces to 3 out of 8. So there's a 3/8 chance of having 2 boys and 2 girls, given that you have a family of 4. So list the sample space, as we'll do for this one. I just mentioned coin flipping. Suppose you flip a coin 3 times. Or I believe there's a question in your homework assignment that says you flip 1 penny, 1 nickel, and 1 quarter, or something like that. And I want to figure out what is the probability of these outcomes. I flip a coin 3 times. What's the probability of having exactly, let's see, I'm looking at tails exactly 1 time, 0 times, or at least twice. And of course, if I start listing them, tails, 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 heads, tails, heads, tails, etc., etc., I've got them all listed out to save myself time in this video. These are the 8 possible outcomes. 2 times 2 times 2, if you want to look at fundamental counting principle. And once I've got the sample space listed out, answering these questions should be pretty easy. Exactly 1 time, let's see, I count this one here, and this one. I think all the rest of them have either too few tails or too many tails. So 1, 2, 3 out of the 8 possibilities of getting exactly 1 coin flip of tails. Probability of tails coming up 0 times, well, that's only 1 possibility. 1 out of the 8. And having at least 2 tails, let's see, I can circle these now since I'm at the end of the problem. These 4 possibilities have at least 2 tails. 2 tails or more than 2 tails. In this case, let's see, that was 4 out of the 8, which in the interest of making these notes make sense to someone who doesn't watch the video, that 4/8 will reduce to 1/2. So there we go. And then finally, let's take a look at rolling dice, a staple of probability questions. If I say, what are there, or how many outcomes are in the sample space for rolling 2 number cubes? I think if I call them dice, I'm promoting gambling. So I don't know. If it's okay with you guys, I'm going to keep calling them dice, but in my presentation, for legal reasons, I'll call them number cubes. So I can have plausible deniability when one of you turns 18 and goes to Mystic Lake and decides to put all of your money on 7 or something like that. But anyway, how many outcomes are in the sample space? Here again, you might look at this and experienced Monopoly players would say, well, the lowest possibility is 2, and the highest possibility is 12, and it could be anything in between. So let's see, that's 11 possibilities. There's 11 outcomes. And I understand what you're saying when you say that. That is not the number of elements in the sample space. And I'm going to roll these dice and see if I can get an outcome that's fairly likely. Here's a roll of 2 and 4. Now you might look at this and say, well, that's an outcome of 6. Well, yeah, but that's a 2 and a 4. That looks different than if I roll. We'll see if I can roll another 6. I should have chosen 7. I just had 2 in a row. Well, look at that. I got 2 and 4 again. So this is an outcome. I've seen, this outcome twice already, but that's not the only way to have a sum of 6. There's another one. A 5 and a 1 would also be a sum of 6. And so those outcomes are not equally likely. It's more likely for me to roll a sum of 6 than it is to roll a sum of 2 because there's only one way. We'll see if I can do it in a couple of rolls. There's only one way of rolling a sum of 2, and that outcome only happens if I roll a 1 on both of the dice. Now, I'm not going to waste too much time trying to do that because there is only one way of rolling a sum of 2. These are all the possible outcomes. 1 and 1, 1 and 2, 1 and 3, 1 and 4, etc., 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 all the way down to 6 and 6. And if you're looking at this and you're thinking, well, Mr. Crow, aren't these the same outcome, a 4 and a 1 and a 1 and a 4? My response, and I don't remember who told me this, it was probably one of my teachers at some point who said, if I'm playing Monopoly with 2 different colored dice, it doesn't change the probability of any of the outcomes. I'm not more likely to roll a sum of 4 if I have 2 different colored dice versus the same colored dice. And so you have to list those as 2 different outcomes. Now, a red 1 and a blue 1 is the same as a blue 1 and a red 1. Those look the same. That is the only way that you roll a sum of 2. We have to treat 1 and 4 and 1 differently. And then a couple things that I'll point out about this sample space. You'll see this sample space multiple times. If we go across these diagonals, there's your sum of 2, here's your sum of 3, here's your sum of 4, all the way up to the one that's the most likely is a sum of 7. There are 6 different ways of rolling a sum of 7, and then after that, numbers start decreasing again. There are 4 ways of rolling a sum of 9. If any of you play Settlers of Catan, this is why robber moves with the 7. That's the most likely outcome. None of the collections happen with the 7, because that would happen too often. It would throw off the game. And if you've got the robber sitting in one of your territories, you want that 7 to come up quickly. Anyway, if you never played Settlers of Catan, none of that made sense. That's all right. So let's take a look at some probabilities. I'll look at the probability. We'll take a look at union and intersection. I could write the questions like this. On your homework assignment, you'll see some questions where it just says, what's the probability of rolling a sum of 7? One of the dice shows a 3. Or I may use this notation. Now, I'm going to try to help get you guys used to this notation. So I'll do this slide. But the slide is exactly the same as the previous slide. That was written out in words. This one's written out with symbols, but it means the same thing. Probability that there is a sum of 7, I guess I already outlined that a couple slides ago. That is these 6 different outcomes. There are 6 different ways to roll a sum of 7. So out of the 36 possibilities, 6 of them are a sum of 7. So 1 out of every 6 rolls is probably going to be a 7. Now, of course, if you roll the dice 6 times, you're not guaranteed to get a 7. But it's fairly likely that you would. I mean, you could roll 1 and 1. You could roll snake eyes 18 times in a row. It is extremely unlikely, but I suppose it's mathematically possible. The probability that one of the die shows a 3. There's a 3, there's a 3. And I specified on this problem that one of the dice, I'm going to go and make sure, one of the dice shows a 3. So I didn't say at least one, I said 1. So we'll count all of these. We'll count all of these, but I'm not going to count one where there were 2 3s because I'm picky about this. If I want to count that one, I would have said at least 2 of the dice show a 3. So what do we have? 2, 4, looks like we've got 10 total. 10 out of 36, which would be the same as 5/18. And now union and intersection. Probability that the sum is a 7 or a 3 shows. Well, I've got one circled already. I'm actually going to erase that one. I don't want to get confused by that one. I'm not including that one as a dice or one of the dice showing a 3. And I'm also going to count up my 7. So I've got those 2 that I haven't counted yet, and those 2 that I haven't counted yet. So in the or category, I've got some rolls that are a sum of 7. I've got some rolls that show a 3. And then I've got a couple rolls here, 4, 3, or 3, 4. Those would be in both categories. I count them equally. So I've got the 10 that I counted before, plus 2 more, plus 2 more. I should have 14/36, which is a weird word to say. That would be the same as 7/18. And then finally, maybe I'll color code this one. Rolling a sum of 7 and one of the dice is a 3. Those are the only possibilities. We've got 2 out of 36 or 1 out of 18. So if you need a 3 as one of the dice, a sum of 7, there's only a 1 in 18 probability of that happening. And now finally, if the only new notation that you learned today is this one, little c as a superscript stands for the word complement. Now in geometry, you use the word complement. A 60-degree angle is complementary to a 30-degree angle. A 45-degree angle's complement is another 45-degree angle. Complement in this context means a similar thing, but instead of completing 90 degrees, we're using complement to complete 100%. Another way to think of it, and the way that I think is probably going to be the most helpful to you guys, is to think the word not. In a simple example, I'm going to go with the probability that I roll a sum of 7. We saw earlier that that was 1/6. Well, if the probability of rolling a 7, then the probability of the complement, and you see my superscript down here, don't miss that. That's a big deal when you see that little C show up. This is the probability of not rolling a sum of 7. So if it's a 1 in 6 probability of rolling a 7, then it's a 5 out of 6 probability of not rolling a 7. And we could do this by going back to the sample space for rolling dice, and I could count all of these up. I could count all of the ways that there are of not rolling a sum of 7. There's a lot of them. I suppose there's 30 of them here. I think I've got 15 members of the sample set in each one of those, and so 30 divided by 36 would reduce to 5/6. Of course, the easier way of doing that is just subtracting from 1. The probability of a sum of 7 is 1 out of 6, then let's take 6/6 or 1 and subtract 1/6 to get the rest of them. Okay, and then one last example of that. This also works if I've got something like this. What is the probability that I roll a sum of 7 or a sum that is less than 4? Well, I've got my sum of 7 in the diagonal. These are the only ways. There's 3 ways of rolling a sum that is less than 4. So if I say, what's the probability of rolling a sum of 7 or a sum that is less than 4? That's 6, 7, 8, 9. 9 out of 36, which reduces to 1/4. And so if I say, what's the same probability, but I put the little c there, that's my way of saying, what's the probability of not rolling a sum of 7 or a sum that is less than 4? And so if the probability of that happening is 1/4, the probability of it not happening is 3/4. And by the way, I'm actually going to duplicate this slide really quickly. It just occurred to me that we can do one more quick example that'll maybe help someone understand what we're doing. If I change just that symbol from a union to an intersection, I have to go and get this crazy character. And I'm actually going to copy it so I can paste it down here. I should have had this ready to go. So I'm changing the question. What is the probability of rolling a sum of 7 and a sum that is less than 4? Well, we saw this. The 7s are all along the diagonal. The sums that are less than 4 are over here. What is the probability of rolling both of these at the same time? Here's our 0 probability. And if the probability of something is 0, then the probability of its complement will be a 1. If I roll 2 dice, the probability of me not rolling a sum of 7 and a sum that is less than 4 is 1. It's going to happen every time, because it's impossible for that outcome to happen. It's certain that outcome not happening is going to occur, if that makes any sense. Well, hopefully that makes sense. If there are questions about this, of course, as always, you can pop by my office hours between 2 and 3 o'clock, or send me an email, or of course, if there are questions, we can talk about them on Monday as well. Okay, I'm going to get this posted for you guys ASAP so you can work on it hopefully on Friday. Otherwise, you'll have to do it sometime this weekend. Have a great weekend. Stay warm. It's cold outside. We'll see you on Monday.